Okay, so line integrals. So we've talked about line integrals. I've done plenty of examples, maybe not plenty, but quite a few examples for the past couple days. And let's think about what do they actually represent. So if we have some curve, when I'm talking about a line integral for vectors, right? So this is the f dot dr one. It means that at every point along this curve, I have a vector. It doesn't really matter what direction they're pointing in. Let's just say it looks something like this. And this is at every point, not just these ones that I'm picking out. Let's put that this way. Okay, so each of these vectors has a tangential component, right? The length of this vector, right? Each of these vectors has a component in the tangential direction, right? That's going to be f dot the tangent vector, or f dot r prime. Okay, so that's what each of these represents. So this component, right, the length of this tangential vector is a function of where we're at on the curve. It's a function of t. Okay, so when we do this integral, what we're doing is we're adding up the length, or you're integrating this component of the vector. So we're kind of adding up all of these components together to figure out what is the total amount of these vectors in the direction of this curve. Okay, so when we do this, a lot of times we'll have some kind of weird domain. Something like this, like you see over yeah, something like this, like you see over here on the left, right? Where we kind of have it in a bunch of different parts, right? We kind of have this portion, we have this portion, we have this portion. And the way I would do this is I would have a parameterization for each of them, right? So I'd split this up, so the integral over C, the whole curve, would be the integral of C1 plus, and then I do the same thing, but I do C2. I do the same thing for all of them. Okay, so I do the same thing for all of them, but that's a real pain. Okay, especially if you have like a lot of different curves, or maybe they're rather complicated. They can be complicated to integrate. Um, so what we want to do is figure out ways to make these easier to integrate, right? Because there's a lot of shortcuts in how we can integrate them for different types of functions. Okay, so the first one we looked at last time, and I'm going to do some actual examples. Okay, so these are ones where, let's see, is this the one I want, or is it? Yeah, so these are ones where we can write this as functions where we can write this as the gradient of something else. Actually, is that where I got this problem? Hold on, make sure I'm in the right section. Number 12. Yeah. Okay, it's because if we can write a function as a gradient of something else, right? So if we can write f equals the gradient of some potential function, then the integral of f um, from point A to point B, whatever this is, whatever the coordinates are, dot dr, this basically just becomes integrating the gradient of f dot dr from point A to point B. And real quick, when I say point A and point B, that just means like the start and end. Okay, so that might be whatever the x and y coordinates are, or whatever the t value is. It doesn't really matter. But when we integrate this, this is going to be just f at b minus f at a. So if we could write f, capital F, as the gradient of some potential function, then this integral over here on the left, whatever integral it is, it's really doesn't matter. I just need to evaluate the function here, and that's it, right? So I don't have to worry about all this parameterization. So that's nice. And let's do a couple examples of that. Okay, so here we want to see, can we write this as the gradient of something else? I'm just going to sketch this curve. So 2x squared looks like this. And then we want to go from here to here. So we don't really care about this region over here. This is the region we're interested in. Okay, so to check if we can write this as a gradient, so we did this a while back. All right, so this is x squared, y squared. I'm going to look at the second derivatives. Okay, so I look at the x derivative. Oh, sorry, I look at the blah. Okay, so I'm going to assume for a second, assume that this is the gradient of, let me call this p for a potential, but just assume that, no, that's confusing. Little f. Okay. So in context of notes and stuff that you've seen in the class, this is P and this is Q. Okay, so we're assuming that this is equal to the gradient of something, right? So that means that df dx is equal to x squared, and then df dy is equal to y squared. Now, I'm going to look at the mixed derivatives. So I'm going to take the y derivative of this one. So that's the y derivative of x squared, which is just 0. And then I take the x derivative of the y derivative. So dy, which is also going to be 0. Since they are the same, that means that I can write this function. It means that this f actually exists. Okay, if I found that they were different, then it wouldn't be possible. Okay, so that's actually a fairly quick check, right? You just compute like two second derivatives, or actually you don't even have to do that. You just do like a derivative, the y derivative of this one, and then the x derivative of this one, and check if they're the same. Okay, so this one is, so let me figure out what can I write this as the gradient of. So if I know that df dx equals x squared. So if I integrate this with respect to x, give myself some room. So if I integrate this with respect to x, I get x cubed over 3 plus some function involving y, so stuff that involves y. Because remember, as far as x is concerned, y is a constant, right? When I do the partial with respect to x, y is a constant. So same thing when I integrate dx plus some actual constant. And same thing for the y component. So this is integral of partial with respect to y dy. So that's integral of y squared dy, and I get, equals y cubed over 3 plus some function involving x plus some other constant. Okay, so now I'm going to write down any terms that are in both of them. So there's nothing that's in both of them. And then I'm going to write down all the terms that involve only x, right? So that's kind of what is this? So I don't know what this is, but I look over here. And the terms that involve only x, that's going to be x cubed over 3. And then I look for the stuff that involves only y, right, that stuff. That's going to be this function right here, plus some constant. Okay, so now I know that this is my f of x and y, and I want to integrate it from here to here, right? So that means I just need to evaluate this, the integral of f dot dr from the point, what was the point? It was negative 1, 2, negative 1, 2, all the way up to 2, 8. Yeah. So this is my A, this is my B. So this is just going to be f of minus 1, 2 minus f of 2, 8. And so this constant is going to cancel out in either case. So what I'm going to end up with is, let's see, so we're going to have negative 1 cubed over 3 plus 2 cubed over 3 minus 2 cubed over 3 minus 8 cubed over 3. And then the c's cancel out, right? So I would have plus c and then also minus c, so they cancel out. Did I do it back? I did do it backwards. You're right. Real quick, do y'all hear that noise in the background? No, my mic's not picking it up. Okay, good. Yeah, so this should be the other way around. 2, 8 minus 1, 2. Okay, so all that does is just change the sign. So this is negative, this is negative, that's positive, that's positive. Those still cancel out, so I end up with 8 cubed. That's what? That's 64? No. 8 times 8 is 64, times 8 is 256. I believe that's right. 256 over 3 um, minus 1/3, so that's plus 1 over 3. 257 over 3, and that's not divisible by 3. And that's my answer. So evaluating this curve, I didn't have to parameterize this line at all. I just found that since this was the gradient of something else, I can use this fundamental theorem of line integrals, and it becomes very easy. Right, so this is kind of like when you first learned about how to do an integral, right? You don't have to do Riemann sums anymore. You can just kind of do the antiderivative of both sides and evaluate it at the endpoints. So that's kind of what this is equivalent to. Okay, let's do one more. So here, let's see if we can write this as the gradient of something. So again, I'm going to have f, which is y squared over 1 plus x squared, and 2y arctan of x. And I'm going to assume for a little bit that this is the gradient of some function. Okay, so now I do the y derivative of the x component. All right, so this is df dx, this is df dy. And then I do the y component, or the y derivative of the x derivative. So that's going to be 2y over 1 plus x squared. So that's df dy dx. And over here I do the x derivative of the y derivative, and that's going to be the same thing, 2y over 1 plus x squared. Okay, since they're the same, right, since they're the same, that means that this function actually exists. If I would have found that they're different, it means that this function doesn't exist. Okay, I need to do something else to integrate these. Okay, so what is this function? So if I integrate this with respect to x, I get, um, if I integrate this, I get arctan, so I have, that's going to be arctan, I guess, y squared arctan of x plus a constant. And then I integrate this one with respect to y. Um, sorry, so this is plus stuff that involves only y. And then when I integrate this one, I integrate this with respect to y. I get f of xy is same thing plus some function that involves x plus c. Okay, so now I can write my function. First, I choose the terms that are in both of them, right? So that's going to be this thing right here. So this is y squared arctan of x. And then I look for any functions that involve only x. So, right, I'm looking for this. So I look in this top one, and there's no functions that involve only x. Okay, so basically I'm done. And in the bottom, there's no functions that involve only y. So there's no functions, kind of that involve only y plus c. Okay, so this tells me that integral f dot dr from, it tells me, oh, it gives me parameterization. Okay, so it's not terribly hard. I'll just go from t equals 0 to t equals 1. This is equal to, um, sorry, they're mowing the lawn outside my window, and it's very annoying and distracting. Okay, where am I at? This is, this is, wow, that is annoying. One second. There can't be that much grass outside there. Okay, sorry. So we have the x or f of r of t. So I'm going to plug in what is this? So r of t of 1 minus f of r of 0. So this is 1. Okay. So I can do this. I can either plug t into r to get my x and y coordinates, or I can plug the x and y coordinates into here and then just plug in t as well. I think I'm going to do it the other way. So r of 1. So if I plug in 1, I get 1, 2. So that's 1, 2. And then if I plug in 0, I get 0, 0. Right, so I'm plugging in 0 in to here, right, to my r. And I'm also plugging 1 into the r. And that's where I get the 1, 2 and the 0, 0. Okay, so I evaluate these. This is arctan of 1. The angle whose tangent is 1 is what? Somebody answer. Arctan of 1 is what? Somebody answer. Pi over 4, thank you. Pi over 4 times y squared, so that's going to be times 4, minus 0, arctan of 0 is 0, y 0 squared is 0. So this just equals pi. Okay, so that is the fundamental theorem of line integrals. So remember, this right here is called a potential function, and this over here is, if this function exists, we call f, big F, a conservative vector field. Okay, so next topic. Now, again, we're still looking for ways to integrate line integrals a lot easier. Okay, so now we're going to be looking at um, curves that they can be very strange, but the point about them is that they go in an that's a bad example. They go in an entire loop. Okay, so if I had some vector field, so suppose this is A, and suppose it was conservative, okay, and I do the integral all the way around this loop. What does that mean? Okay, so the way we write that, when we want to say that we go all the way around the loop, we write that as a circle. Okay, that's what this means. It means that we're starting at some point and we're integrating this function all the way around a closed loop. Sometimes they put a little arrow to indicate the direction. It just means that we're going around in the counterclockwise direction. Okay, but generally it means the same thing. And if it doesn't have a direction, just kind of assume that it's going counterclockwise. Okay, so if this was conservative, then I would pick a point, then what are my bounds, right? I'd be integrating from point A all the way around to point A. So this would just be f of A minus f of A, right? Whatever my A is, which would be 0. So if I go around a closed loop with a conservative vector field, this integral is going to be 0. Okay, so that's nifty. But let's look at now integrals that aren't conservative. Okay, we're going to be interested though in the case of where we're going around an entire closed loop. So no more ones where it's just a segment. Now we have to be going around a whole loop, right? So we have the boundary. Real quick, I haven't watched through all of the lectures. What symbol does Dr. Wagner use for um, the boundary? Does he talk about the boundary, or does he just say C? Anybody know? Otherwise, I'm gonna make up a notation right now. Okay, so here I'm gonna call this region on the inside. I'm gonna call this omega, and then on the boundary, typical notation is gamma. Right? That's gonna mean the boundary of this area on the inside. Okay, so this is yeah. This means the boundary. Okay, so what we have is this. If I integrate along all the way around the boundary of some region, okay, this is going to be the let's write it this way: F equals P Q. This is going to be the integral over my domain of, let's see, it's going to be dq dx minus dp dy yeah, dA. So this is actually pretty cool because it just turned this surface integral, sorry, not surface integral, this line integral, right, where we're going around, it just turned this integral into a double integral. Okay, and double integrals are usually, I'll say in a lot of cases, they're easier to integrate, especially if you can use like polar coordinates or something. Um, But yeah, so it's a way to convert a line integral into a double integral over the area. Okay, so let's see an example. Okay, 1 second while I copy an example. Mm, Let's see. That one looks fine. So I'm going to do a really simple one first, but I hope it gets the idea across. Okay, so first off, what is this weird notation with the dx and the dy? Um, Technically what this means, so I have, okay, so they use c. This is x minus y. I'll put x prime dt plus x plus y y prime dt. Right, this is dx dt, actually not y prime. Let me write it as, just to make sense. Now this step that I'm doing right here, it's not necessary at all. I'm just explaining what you're looking at. Okay, so this is dy dt. Okay, so if I factored out the dt, then I have x minus y times dx dt, or plus x plus y dy dt multiplied by, or integrated with respect to dt. Now this is the same as x minus y x plus y dot dx dt dy dt. Okay, and that's the same as f, right? This is my f dot r prime dt. So this is just another way, it's just another notation for writing f dot r prime, or f dot dr. Right? It's just another way of writing the same thing. So everything still applies. These are the components of f. This is going to be my p. This is going to be my q. We could check and see if this is a conservative vector field, but it's not going to be. Right, so if I do the derivative of this with respect to y, I get -1. If I do the derivative of this with respect to x, I get +1. Not the same, not conservative. Okay, but what I can do is I can turn this into a double integral. So this integral along the boundary of the circle of radius 2 turns into the double integral. So let me just write it this way, of f dot dr. Okay, and I didn't have to do all of these steps at all. It was just for me to show you that this is the same as this. Okay, but f dot dr, that's going to be the same as the double integral over the circle, right, over this entire region of, so I do dq dx minus dp dy dA. So let me compute those derivatives. So this is going to be integral of, so derivative, that's going to be y minus, I'm sorry, that should actually be 1. This should be 1 minus the derivative of this with respect to y. That's going to be another 1. Oh, so minus minus is a positive. So that's the double integral of 2 dA for omega. So this is actually really easy to compute. I don't need to actually do any integrating. If I bring the 2 out, I have the double integral of times 1 dA. And what does this represent? Does anybody recognize what this represents or why this would be easy to compute? Yeah, not pi, yeah, pi r squared. It's the area of the region, right? So our region is a circle of radius 2. So this is going to be 2 times pi times 2 squared. So I get 8 pi. Okay, and that's going to be my line integral of this vector field around the boundary of this circle. Okay, next one, let's do one that's a little bit harder. Okay, let's do that one. Okay, so I'm just going to sketch this because I'm going to have to sketch it in the end eventually. So y equals x squared, that looks like this. And then x equals y squared, looks like this. Right, so this is the region I'm interested in. So I have my f, right, that's going to be pq, just for reference. This is going to be y plus e to the root x, 2x plus cosine of y squared. Yeah. Okay, so if we were to actually just try to integrate this along the line, it would probably be pretty difficult. Okay, but we can do the transformation, so this becomes so C is the boundary of the region enclosed by the two parabolas. Yeah, so this is the integral all the way around this region, f dot dr equals. So I can use, does anybody remember what this is called? The name of this trick that I'm using? It's got a name. So this right here, this is called Green's theorem. Okay, so um, Green was actually one of the first people to try to actually figure out the laws of electromagnetism. So we hear about Maxwell and Maxwell's laws and other stuff like that. But Green was the first one who tried to actually, figure this stuff out. Um, so really all of the rest of the stuff that we do this semester, it was all invented specifically to describe um, electricity and magnetism because it works very nicely for that. Okay, so back to this. If I do the derivative of q with respect to x, I get 2. Yeah. And then derivative of this with respect to y. Really? That's another easy one? Okay, fine. dA. So I do need to figure out the area of this region. So usually they're not going to come out, I don't expect that they would come out this easy. So that's 2 minus 1, that's 1 dA. But I should figure out what are the bounds. So if I just integrate along vertical strips, well, I can just do a regular integral, but I'll set up the double integral. Right, so we pick a integrate with respect to y first. That's going to go from bottom is x squared, from y equals x squared all the way up to y equals root x 1 d dy, and then we integrate all of those strips from 0 up to where they intersect at 1. Okay, so we integrate that and we get integral from 0 to 1 of root x minus x squared. So if you remember Cal 2, this should look familiar, right? The integral of top minus bottom from 0 to 1. And then we get, let's see, so root x, that becomes 2/3 x to the 3/2 minus x cubed over 3 from 0 to 1. That's 2/3 minus 1/3, 1/3. Okay, how much time do I have? Oh, I've got plenty of time. Let's try one more. I do the... Yeah, okay, you know what, that one looks good. Real quick, so he didn't post the notes for today or for Monday, so and I haven't had a chance to go through the lectures, or to watch through all the lectures. Did he move on to curl and divergence yet? Did Dr. Wagner move on to curl and divergence? Do those sound familiar at all? No? No? Okay. I'll assume silence is a no, but let's go ahead and move on to this one. Okay, so here again we want to integrate around this loop, around the boundary of this domain of f dot dr. Right, so f is going to be these components. So this becomes the double integral of, right, so this is going to be the, let's see, so it's going to be dq dx minus, wait, yeah, okay, dp dy. I'll figure out the region in a little bit. So I integrate this, and I get 2 minus 2 x squared minus, I'm sorry, 3x squared minus 3y squared. Okay, so I can write this minus 3 of x squared plus y squared. Over the circle, x squared plus y squared equals 4. Okay, so this sounds like I should use polar coordinates, right? Because if this is my region with a radius of 2, I see x squared plus y squared in 2D, so I think polar coordinates. Let's go ahead and translate. So here I want to integrate this. I'm integrating r squared times r dr. The radius goes from 0 all the way out to 2. And then theta goes from 0 all the way around to 2 pi. Okay, this is separate. This is d theta. This is separable, so I have my, minus 3 integral from 0 to 2 r cubed dr, integral from 0 to 2 pi d theta, which gives me minus 3 times r to the 4 over 4 times 2 pi for a final answer of, let's see, so it's going to be 2, 4, 8, 16 over 4. That's 4. So that's minus 3 times 4 times 2 pi is minus 24 pi. Like that. Okay, any questions? Okay, before I get ahead, let me look at what's next in the textbook. Don't know. Okay. That means probably a no, but oh no, he moves on to oh, okay, so this is in a different order. Surface integrals. Okay, so did he do surface integrals? Does that sound familiar? Um, surface integrals. Okay. How about this then? Any questions from the homework or review? So the homework is due on Friday. I will be on, this evening if you guys have questions, or tomorrow evening, just post a question. Um, Otherwise, I think that's a good stopping place, unless anyone has questions, or has a question they'd like me, or a topic they'd like me to go back to. No? Okay. Um, so in that case, I guess I'll cut it off a little bit early. Um, yeah, okay. I will see you all on Friday then.